A black hole is born when a very massive star reaches the end of its life and collapses under its own gravity. Throughout its life, a star balances two powerful forces. Gravity constantly tries to pull the star inward, while the intense energy from nuclear fusion in its core pushes outward. For millions of years, these forces stay in balance, but eventually, the star runs out of fuel. When that happens, the outward pressure disappears. Gravity suddenly wins. For extremely large stars, usually at least 20 times heavier than our Sun, the collapse becomes unstoppable. The star's core crashes inward at incredible speed. Imagine something the size of Earth being squeezed down smaller and smaller in just seconds. The pressure becomes so extreme that the core compresses into an incredibly tiny, dense point. At that moment, gravity becomes so powerful that a black hole forms. It's like the universe taking a giant star and crushing it into the darkest object imaginable. Black holes are so incredibly dense that nothing, not even light, can escape their gravity. To understand how extreme this is, imagine the strongest rocket ever built trying to launch from Earth. It must reach a certain speed, called escape velocity, to break free from Earth's gravity. A black hole takes this idea to the absolute limit. Its gravity is so strong that the escape speed becomes greater than the speed of light itself. And since nothing in the universe can move faster than light, escape becomes completely impossible once something gets too close. Even light, which normally travels about 300,000 kilometers per second, fast enough to circle Earth more than 7 times in a single second, cannot break free. This is why black holes appear perfectly dark. They don't reflect light, and they don't let light leave. Instead, they trap it forever, making them some of the most mysterious objects in the universe. Around every black hole lies an invisible boundary, called the event horizon. This is the exact point where escape becomes impossible. If anything crosses this boundary, whether it's a rock, a spaceship, or even a beam of light, it can never return. You can imagine the event horizon like the edge of a giant cosmic waterfall. If a boat floats safely upstream, it can still turn around and paddle away. But once it drifts past the edge and begins going over the waterfall, there is no way back. The event horizon works in a similar way. Outside the boundary, objects can still escape if they move fast enough. But once they cross that invisible line, gravity becomes overwhelming. What makes it even stranger is that the event horizon isn't a solid surface. There's nothing you could touch. It's simply the point where gravity becomes so powerful that the universe itself offers no escape. For decades, black holes were only theoretical objects. Scientists were sure they existed, but no one had ever actually seen one. That finally changed in 2019, when astronomers revealed the first real image of a black hole. This historic picture was captured by a global network of telescopes called the Event Horizon Telescope. Instead of one giant telescope, scientists connected radio telescopes around the world, from Hawaii to Chile to Antarctica, so they worked together like a single Earth-sized camera. The image showed a glowing ring of hot gas surrounding a dark circular shadow. That dark center is the black hole itself. The ring looks like a fiery donut floating in space, glowing brighter than entire star systems. What we're actually seeing is superheated gas swirling around the black hole just before it disappears beyond the event horizon. It was one of the most important astronomical images ever captured. The first black hole ever photographed in 2019 sits at the center of a giant galaxy called Messier 87, often shortened to M87. This galaxy lies about 55 million light-years away from Earth. That means the light used to create the famous image actually began its journey when dinosaurs had not even appeared on Earth yet. Messier 87 is an enormous galaxy, far larger than our own Milky Way, containing trillions of stars. At its very center hides the massive black hole that produced the historic image. even from such an incredible distance. Astronomers were able to detect the glowing ring of superheated gas swirling around it. Capturing this image was like trying to photograph a tiny orange placed on the surface of the moon while standing on Earth. Yet, with the combined power of telescopes around the world, scientists managed to do exactly that. The black hole photographed in 2019 is unbelievably massive. It weighs about 6.5 billion times more than our Sun. To understand how huge that is, imagine taking the mass of the Sun and multiplying it 6.5 billion times. That's like stacking billions of stars together into one single object. If our entire solar system, every planet, moon, asteroid, and comet were placed near this black hole, its gravity would completely dominate everything. Yet despite holding the mass of billions of suns, the black hole itself is not infinitely large. Its event horizon is roughly the size of our solar system. That means all that enormous mass is squeezed into a region only about as wide as the distance from the Sun to Pluto. It's like compressing billions of stars into a space the size of a cosmic neighborhood. The density is almost impossible to imagine. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. At the very center of our own galaxy, the Milky Way, there is a giant black hole called Sagittarius A star. Even though we cannot see it directly with our eyes, astronomers know it's there because of how stars move around the galaxy's center. Imagine watching leaves swirl around a hidden drain in a pool. Even if you cannot see the drain itself, the motion of the water reveals where it is. The same thing happens in space. Near the center of the Milky Way, stars race around an invisible point at incredible speeds, millions of kilometers per hour. Only something extremely massive could pull stars into such tight, fast orbits. That hidden object is Sagittarius A star. It sits about 26,000 light years from Earth and acts like the gravitational anchor of our entire galaxy, quietly holding billions of stars in its influence. The supermassive black hole at the center of our galaxy, Sagittarius A star, has a mass about 4 million times greater than the Sun. That means the weight of 4 million stars like our Sun is packed into a single, invisible object. To picture how extreme this is, imagine squeezing 4 million suns into a space smaller than the orbit of Mercury, the closest planet to our Sun. All that mass is compressed into a region only about 44 million kilometers across. That may sound large, but in space terms, it's surprisingly small. Despite its enormous power, Sagittarius A star is relatively quiet compared to some other black holes in the universe. It isn't currently swallowing huge amounts of matter. Still, its gravity controls the motion of stars in the central region of the Milky Way, acting like a massive invisible engine at the heart of our galaxy. Black holes don't just pull on objects with gravity, they actually warp the fabric of space and time itself, something scientists call space-time. According to Einstein's theory of relativity, massive objects bend space-time around them, and black holes do this more extremely than anything else in the universe. A helpful way to picture this is to imagine a stretched rubber sheet. If you place a small ball on the sheet, it makes a small dent. But if you place something extremely heavy, like a bowling ball, the sheet sinks deeply around it. A black hole is like dropping the heaviest object imaginable onto that sheet. The dent becomes so deep that space-time curves dramatically inward. Anything moving nearby, stars, gas, light, must follow that curved path. Instead of traveling straight, they spiral toward the black hole because space-time itself has been bent into a steep cosmic funnel. Near a black hole, time itself begins to slow down. This strange effect comes from Einstein's theory of relativity, which tells us that strong gravity affects how time passes. The closer you get to a black hole, the stronger the gravity becomes. As gravity increases, Time starts moving more slowly compared to places farther away. For someone near the black hole, time would feel completely normal. Their watch would tick at the usual pace, but to someone watching from far away, that person's clock would appear to slow down more and more. Imagine two identical clocks. One stays safely far from the black hole, while the other moves close to it. When they are compared later, the clock near the black hole would show less time has passed. In extreme cases near the event horizon, a few minutes near the black hole could equal years far away. Time itself stretches under intense gravity. If you fell toward a black hole, something very strange would happen. From the point of view of someone watching from far away, to them, it would look like you slow down more and more as you approach the event horizon, until you appear to completely freeze in place. This happens because the black hole's gravity slows time dramatically near its boundary. As you get closer, the light carrying your image back to distant observers becomes more stretched and delayed. Imagine watching a video that slows down until every frame takes longer to appear. Eventually, it would look like the video has paused. That's similar to what observers would see. To them, you would never actually cross the event horizon. You would appear stuck right at the edge, slowly fading and dimming over time. But from your own perspective, you would keep falling inward normally. The universe outside would simply appear to speed up. A teaspoon of neutron star material is already unbelievably heavy, but the density inside a black hole can be even more extreme. Neutron stars form when a star collapses so tightly that atoms are crushed together. In that state, a single teaspoon of neutron star matter would weigh about 1 billion tons, roughly the weight of a mountain. Black holes push this idea even further. When a massive star collapses past the neutron star stage, gravity keeps squeezing matter inward without stopping. The material becomes compressed into an incredibly tiny region. It's like taking the mass of a star, something millions of kilometers wide, and crushing it into a point smaller than a city. The density becomes so extreme that our normal understanding of matter begins to break down. Physics as we know it struggles to describe what happens inside. That's one reason black holes remain one of the greatest mysteries in the universe. Many black holes begin their lives as stellar black holes, which form when extremely massive stars die. These stars must usually be at least 20 times heavier than our Sun. During most of their life, they burn enormous amounts of fuel through nuclear fusion, producing huge amounts of energy that push outward against gravity. But massive stars burn their fuel very quickly. When the fuel runs out, the outward pressure suddenly disappears. Gravity then takes over, and the star collapses inward with incredible force. The outer layers may explode outward in a powerful supernova, one of the brightest explosions in the universe. But the core continues collapsing. If the remaining core is massive enough, it compresses so tightly that nothing can stop the collapse. The result is a stellar black hole. It's like a giant star suddenly losing its internal support and falling inward on itself in just seconds. Many people imagine black holes as giant cosmic vacuum cleaners that suck in everything around them. In reality, black holes don't work that way at all. Their gravity behaves just like the gravity of any other object with the same mass. If our Sun were magically replaced by a black hole with the exact same mass, Earth would continue orbiting almost exactly the same way it does today. The planets would not suddenly get pulled in. Gravity only becomes dangerous when something gets very close to the black hole. You can think of it like a deep pit. If you stay far away, nothing happens. But if you wander too close to the edge, you might fall in. Black holes mainly pull in nearby gas, dust, or unlucky stars that drift too close. The rest of the galaxy usually continues moving normally around them. For an object to be trapped by a black hole forever, it must cross a specific boundary called the event horizon. Before reaching this boundary, escape is still possible. A spacecraft with enough speed could theoretically turn around and fly away. But once the event horizon is crossed, escape becomes impossible. No rocket, no engine, and no force in the universe could bring the object back out. You can imagine it like drifting toward a powerful waterfall in a river. Far upstream, you can still paddle away, but once you pass the point where the current becomes too strong, the waterfall will carry you over no matter what you do. The event horizon is that point of no return in space. What makes it even stranger is that the boundary itself is invisible. There is no wall or surface, yet crossing it seals the object's fate forever inside the black hole. Black holes are not always quiet, motionless objects. Many of them spin incredibly fast. This happens because the stars that formed them were already rotating before they collapsed. When a massive star collapses into a much smaller space, its rotation speeds up dramatically. It's similar to what happens when an ice skater pulls their arms inward during a spin. As their body becomes more compact, they spin faster and faster. The same idea applies to collapsing stars. As the star shrinks into a black hole, its rotation becomes extremely rapid. Some black holes spin so fast that the outer edge of the event horizon moves at a significant fraction of the speed of light. That's like something circling Earth several times in a single second. This rapid spin affects the surrounding space, twisting and stirring the environment around the black hole. When a black hole spins, it does something incredibly strange. It drags space-time along with it. Instead of space staying still around the black hole, the rotation actually pulls the fabric of the universe into motion. Imagine placing a spinning spoon into a thick bowl of honey. As the spoon turns, the honey around it begins to swirl and twist along with the motion. The faster the spoon spins, the more the honey gets dragged around. A rotating black hole does something similar, but instead of honey, it drags space-time itself. This means that anything near the black hole, gas, dust, or even light, gets forced to move in the direction of the spin. Space itself begins to rotate, close enough to a rapidly spinning black hole. Objects may have no choice but to move along with this cosmic whirlpool. The strange effect where a spinning black hole pulls space-time around with it is called frame dragging. The name might sound complicated, but the idea is surprisingly simple. Imagine placing a spinning ball into a calm swimming pool. As the ball rotates, the water around it starts to swirl and move along with the spin. The faster it spins, the more the surrounding water gets dragged around. A spinning black hole does something very similar, but instead of water, it drags the very structure of space and time. Near the black hole, space-time begins to twist in the direction of the spin. Any object entering this region gets caught in the motion, even if it tries to move in another direction. It's as if space itself becomes a giant rotating current, slowly pulling everything nearby into its cosmic spin. Some black holes don't just swallow matter, they also launch enormous jets of energy out into space. These jets shoot outward from the regions near the black hole's poles at incredible speeds. Before falling into the black hole, gas and dust often form a swirling disk around it called an accretion disk. Inside this disk, matter becomes extremely hot and moves at tremendous speeds. Powerful magnetic fields build up in this chaotic environment. These magnetic forces can redirect some of the material and energy away from the black hole instead of letting it fall inward. The result is two narrow beams of high-energy particles blasting into space. These jets travel close to the speed of light and shine brightly across the universe. It's like a cosmic fire hose powered by one of the most extreme objects in existence. The energy jets produced by some black holes can stretch thousands of light years into space. A single light year is the distance light travels in 1 year, about 9.5 trillion kilometers. That means these jets can extend distances far larger than entire star systems. To picture this, imagine a beam starting at the center of a galaxy and stretching far beyond the galaxy itself. Some jets are so long that they could travel across the entire Milky Way and still keep going. These jets are made of extremely fast particles and powerful radiation. all moving at speeds close to the speed of light. They blast outward in narrow streams from the regions above and below the black hole. In some cases, these cosmic jets become some of the largest structures connected to a single object in the universe, stretching across unimaginable distances. Astronomers have discovered that many galaxies appear to have a supermassive black hole at their center. These black holes are far larger than the ones formed by dying stars. Instead of weighing a few times the mass of the Sun, they can contain millions or even billions of solar masses. The Milky Way is one example, with Sagittarius A star sitting quietly at its center. But our galaxy is not unusual. Observations suggest that this pattern happens across the universe. It's as if galaxies are built around these enormous gravitational anchors. You can imagine a galaxy like a giant cosmic city filled with billions of stars, all moving around a central hub. That hub is often a supermassive black hole. Even though the black hole occupies only a tiny region compared to the whole galaxy, its gravity and activity can influence the motion of stars, gas, and even the galaxy's long-term evolution. Astronomers believe that billions of stellar black holes may exist inside the Milky Way galaxy alone. That might sound surprising, but it actually makes sense when you think about how many stars have lived and died over the galaxy's long history. The Milky Way contains around 100 to 400 billion stars. Among those stars, many are massive enough to end their lives in powerful explosions called supernovas. When the cores of these massive stars collapse, they can leave behind black holes. Over billions of years, this process has likely happened again and again across the galaxy. Most of these black holes are extremely difficult to detect because they are invisible unless they interact with nearby matter. So while scientists have only confirmed a small number directly, models suggest that millions or even billions could be quietly drifting through the Milky Way right now. The closest known black hole to Earth is located about 1,500 light-years away. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. That means this black hole is roughly 14 quadrillion kilometers away from us. While that sounds extremely distant, in cosmic terms it's actually relatively close. Our Milky Way galaxy is about 100,000 light-years wide, so this black hole sits well within our galactic neighborhood. Fortunately, there is absolutely no danger to Earth. At that distance, its gravity has no effect on our solar system. Astronomers discovered this nearby black hole by studying the motion of a companion star orbiting an invisible object. The star was moving in a way that suggested something massive was pulling on it, yet nothing could be seen. That hidden object turned out to be a quiet, stellar black hole. Black holes are not always alone. Sometimes two black holes drift close enough to become gravitational partners, forming what scientists call a binary system. In this situation, the two black holes begin orbiting each other like an extremely powerful cosmic dance. Over time, their orbit slowly shrinks as they lose energy. They spiral closer and closer together, moving faster as the distance between them decreases. Eventually, the two black holes collide and merge into a single larger black hole. This final moment is incredibly violent. In less than a second, huge amounts of energy are released into space. The collision sends ripples through the fabric of space-time itself. It's like two invisible cosmic whirlpools crashing together and becoming one even more powerful vortex. These mergers are among the most energetic events known in the entire universe. When two black holes merge, the collision releases enormous gravitational waves that ripple across the universe. These waves are not made of light or particles. Instead, they are vibrations in space-time itself. You can imagine space-time like the surface of a calm lake. When something large crashes into the water, waves spread outward in every direction. In a similar way, when two black holes collide, they shake the fabric of the universe and send waves traveling outward at the speed of light. By the time these waves reach Earth, they are incredibly tiny. The stretching and squeezing of space can be smaller than the width of a single atom. Yet scientists have built extremely sensitive detectors. capable of measuring them. These signals allow astronomers to listen to cosmic events happening billions of light years away, revealing black hole collisions that would otherwise remain completely invisible. In 2015, scientists made one of the most important discoveries in modern astronomy: the first direct detection of gravitational waves. These waves were detected by an observatory called LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. The signal came from two black holes that had merged about 1.3 billion light-years away. Even at that enormous distance, the collision was so powerful that it sent ripples across the universe that eventually reached Earth. LIGO measures these ripples using two long tunnels about 4 kilometers in length. Inside them, lasers bounce back and forth between mirrors. When a gravitational wave passes through, it slightly stretches and squeezes space itself. The change is unbelievably tiny, about 1/10,000th the width of a proton, yet LIGO detected it. For the first time in history, humanity had a new way to observe the universe, by listening to space-time itself. When black holes merge, the collision doesn't just release energy, it actually sends ripples through space-time itself. These ripples are called gravitational waves, and they spread outward across the universe at the speed of light. To picture this, imagine stretching a large sheet tightly across a frame. If you suddenly shake the sheet, waves move across its surface. In a similar way, when two black holes collide, they shake the fabric of space-time. The waves travel across enormous distances, sometimes billions of light years, before reaching Earth. By the time they arrive, the changes they cause are incredibly small. Space may stretch and squeeze by less than the width of an atom. Yet these tiny signals carry huge information. They reveal the masses of the black holes, how fast they were spinning, and how violent the collision was. It's like hearing the echo of a cosmic crash across the universe. Not all black holes stay inside galaxies. Some of them drift through the vast empty space between galaxies, far away from stars and planets. These lonely travelers move through regions of the universe where there may be almost nothing around them. Most black holes form inside galaxies when massive stars collapse, but powerful cosmic events can sometimes fling them outward. When galaxies collide or when black holes merge unevenly, the resulting gravitational forces can push a black hole away from its original home. Once ejected, the black hole continues moving through intergalactic space, often completely unnoticed. Imagine a dark object wandering silently through an ocean of emptiness for millions or even billions of years. Because black holes emit no light, these wandering objects are extremely difficult to detect. Many could be drifting through the universe right now, without us even knowing they exist. Black holes don't always stay in the galaxies where they formed. In some cases, powerful gravitational events can kick a black hole completely out of its galaxy. This can happen during dramatic cosmic encounters, especially when two galaxies collide and their central black holes eventually merge. When two massive black holes spiral together and combine, the energy released through gravitational waves may not be perfectly balanced in all directions. If more energy shoots out one way than the other, the newly merged black hole can receive a powerful recoil. Almost like the kick from a fired cannon, this recoil can launch the black hole through space at thousands of kilometers per second. That's fast enough to travel from New York to Los Angeles in about a second. If the speed is high enough, the black hole may escape its galaxy entirely and wander alone through intergalactic space. Once a black hole is ejected from its galaxy, it can travel through space almost completely silently. Unlike stars, black holes do not shine with their own light. If there is no gas, dust, or nearby matter falling into them, they become nearly impossible to see. This means a wandering black hole could drift through the universe for millions or even billions of years, without leaving any obvious trace. Imagine a perfectly dark object moving through a vast empty ocean where nothing reflects light. Unless something bumps into it or gets pulled toward it, you would never know it was there. Astronomers suspect many of these silent travelers may exist between galaxies. Some could even be moving through the outer regions of galaxies, unnoticed. Because they are invisible and quiet, detecting them is extremely difficult, making them some of the most hidden objects in the universe. Not all black holes are gigantic monsters, containing millions or billions of suns. Some are much smaller and weigh only a few times the mass of our sun. These are called stellar black holes, and they form when massive stars collapse at the end of their lives. Even though they are considered small compared to supermassive black holes, they are still incredibly extreme objects. Imagine squeezing the mass of several suns, each one over 1 million kilometers wide, into a region only about 20 to 60 kilometers across. That's roughly the size of a city. All that mass packed into such a small space creates unbelievably strong gravity. These smaller black holes often hide inside galaxies like the Milky Way. Some quietly drift through space, while others orbit companion stars and slowly pull gas from them, revealing their presence to astronomers. While some black holes are only a few times heavier than the Sun, others grow into true cosmic giants, weighing billions of times the Sun's mass. These are known as supermassive black holes, and they usually sit at the centers of large galaxies. To imagine their scale, think about our Sun. It is already so large that about 1.3 million Earths could fit inside it. Now multiply that mass billions of times and compress it into a single object. Some of these enormous black holes have event horizons wider than our entire solar system. If one replaced the Sun, its boundary might stretch past the orbit of Pluto. Despite their massive size, they are still extremely dense and invisible. We usually detect them by observing the stars and gas swirling rapidly around them. These giants act like powerful gravitational anchors, influencing the structure and evolution of their entire galaxy. Between small stellar black holes and giant supermassive ones, astronomers suspect there may be a middle group called intermediate mass black holes. These would weigh hundreds to hundreds of thousands of times the mass of the Sun. They would be larger than black holes, formed from dying stars, but much smaller than the monsters sitting at the centers of galaxies. The strange thing is that these middle-sized black holes are very difficult to find. Astronomers have discovered many small black holes and many supermassive ones, but clear evidence for the middle group is still rare. It's a bit like finding tiny ponds and massive oceans, but very few lakes in between. Scientists think these intermediate black holes may hide inside dense star clusters or in small galaxies. Discovering more of them could help explain how supermassive black holes grew so large over cosmic time. Black holes are naturally invisible, which makes them extremely difficult to detect. They do not produce their own light, and once light crosses the event horizon, it can never escape. This means a lone black hole drifting through empty space would be almost impossible to see. Astronomers usually discover black holes only when they interact with nearby matter. For example, if a black hole passes close to a star, its strong gravity can pull gas away from the star. As that gas spirals toward the black hole, it heats up to extremely high temperatures and begins to glow brightly. This glowing material can shine in X-rays, radio waves, or visible light, revealing the hidden black hole. It's a bit like spotting an invisible fan in a dark room by watching the dust spinning around it. The fan itself cannot be seen, but the movement around it gives it away. When gas, dust, or pieces of a star fall toward a black hole, they rarely plunge straight in. Instead, the material usually begins spiraling around the black hole, forming a bright, spinning structure called an accretion disk. You can imagine water swirling down a bathtub drain. The water doesn't fall straight down immediately. It circles the drain in a spinning motion. Matter falling into a black hole behaves in a similar way. As the gas spirals inward, it becomes squeezed and rubbed together by intense friction. This friction heats the material to extremely high temperatures, causing it to glow brightly. In some cases, the accretion disk becomes one of the brightest objects in the galaxy. Even though the black hole itself is completely dark, the swirling disk around it shines like a blazing ring of fire, revealing the hidden monster at its center. The glowing accretion disks around black holes can reach temperatures of millions of degrees. That is far hotter than the surface of most stars. For comparison, the surface of our Sun is about 5,500 degrees Celsius. But gas in an accretion disk can heat up to tens of millions of degrees as it spirals inward. That's thousands of times hotter than molten lava from a volcano. This extreme heat happens because the gas is moving incredibly fast and constantly colliding with other particles in the disk. The closer the material gets to the black hole, the faster it moves and the hotter it becomes. At these temperatures, the disk shines brightly in powerful forms of light, like X-rays. Even though the black hole itself is completely dark, the surrounding disk can glow so intensely that it becomes visible from across vast distances in the universe. Some black holes sit at the centers of galaxies and feed on huge amounts of gas and dust. When this happens, the material forms an extremely bright accretion disk and releases enormous energy. These powerful systems are known as quasars. A quasar is basically a supermassive black hole that is actively consuming matter at a very high rate. As gas spirals inward, it heats up to incredible temperatures and shines with intense light across the universe. The energy released can be astonishing. A region only about the size of our solar system can produce more light than billions of stars combined. Imagine a small glowing point in space, shining brighter than an entire galaxy containing hundreds of billions of stars. Quasars are so bright that astronomers can detect them from billions of light years away, allowing us to study parts of the universe that existed when it was still very young. Quasars powered by black holes can become so bright that they outshine the entire galaxy they live in. This might sound impossible, but the energy released by matter falling into a supermassive black hole can be incredibly intense. When gas spirals toward the black hole, it forms a blazing accretion disk that heats up to extreme temperatures. The disk releases enormous amounts of radiation across many forms of light, including visible light, X-rays, and radio waves. All of this energy comes from a region that may be only about the size of our solar system. Meanwhile, the galaxy around it might contain hundreds of billions of stars, spread across tens of thousands of light years. Yet the tiny region around the black hole can shine brighter than all those stars combined. It's like a single powerful spotlight, glowing brighter than an entire city filled with streetlights. Black holes do more than sit quietly at the centers of galaxies. Astronomers now believe they can actually influence how entire galaxies grow and evolve. When a supermassive black hole is actively feeding on gas and dust, it releases enormous amounts of energy. This energy can heat up surrounding gas or push it outward through powerful jets and radiation. Gas is the raw material needed to form new stars. If too much gas gets heated or blown away, star formation can slow down or even stop. It's a bit like a giant cosmic thermostat. When the black hole becomes too active, it can regulate how much new star formation happens in the galaxy. Even though the black hole itself is tiny compared to the whole galaxy, its energy can affect regions thousands of light years away, shaping the future of billions of stars. In some galaxies, the activity of a central black hole can become so powerful that it prevents new stars from forming. This happens when the black hole releases huge amounts of energy into the surrounding gas. Normally, galaxies form stars when clouds of gas cool down and collapse under their own gravity. But when a supermassive black hole becomes very active, it can heat this gas to extremely high temperatures. Hot gas behaves very differently from cool gas. Instead of collapsing into new stars, it spreads out and becomes difficult to compress. Imagine trying to form a snowball using warm, fluffy snow versus icy, packed snow. When the material is too warm and loose, it won't stick together. In a similar way, heated gas in a galaxy can no longer clump together to form stars. As a result, the galaxy may slowly stop producing new stars altogether. If a star wanders too close to a black hole, it can be ripped apart by the black hole's intense gravity. This happens because gravity becomes much stronger on the side of the star that is closer to the black hole than on the far side. The difference in gravity stretches the star, pulling it longer and longer until it can no longer hold itself together. Imagine grabbing a soft piece of dough and pulling from both ends. Eventually, the dough stretches so much that it tears apart. A star near a black hole experiences something similar, but on a much larger and more violent scale. This extreme stretching effect is sometimes called spaghettification because the star gets stretched into long, thin streams of gas. Once the star is torn apart, some of the material gets flung into space while the rest spirals toward the black hole, creating a brilliant flash of energy. When a black hole tears a star apart, astronomers call it a tidal disruption event. The word tidal refers to the powerful difference in gravity acting across the star. You may have seen something similar with ocean tides on Earth. The moon's gravity pulls on our oceans, creating rising and falling tides. But near a black hole, the difference in gravity becomes far more extreme. When a star passes too close, the side facing the black hole feels a much stronger pull than the far side. This difference stretches the star dramatically. Eventually, the star cannot hold itself together and begins to break apart. The shredded material forms long streams of gas. Some of this gas is thrown out into space, while the rest begins spiraling toward the black hole, producing a sudden and powerful burst of light that astronomers can detect from millions of light years away. When a star is torn apart during a tidal disruption event, the leftover material does not disappear quietly. The shredded gas from the destroyed star begins to spiral around the black hole, forming a temporary accretion disk. As this stellar debris circles closer and closer, it collides with other pieces of gas and heats up dramatically. Temperatures can climb to millions of degrees, causing the material to shine extremely brightly. This sudden burst of light is called a flare, and it can briefly make the black hole's location visible to astronomers. In some cases, the flare can shine as brightly as an entire galaxy for a short period of time. It's like a cosmic signal flare, announcing that a star has just been destroyed. After the debris is finally swallowed or scattered, the light slowly fades, and the black hole returns to being nearly invisible again. Black holes do not only consume stars, they can also capture and swallow enormous clouds of gas that drift too close. These clouds may be many times larger than our entire solar system. Gas clouds often move through galaxies as loose collections of hydrogen and other elements. Most of the time, they simply float through space. But if one passes near a black hole, the black hole's powerful gravity can pull the cloud inward. As the gas approaches, it begins to stretch and swirl, forming a spinning accretion disk around the black hole. Friction and compression heat the gas to extremely high temperatures. This process causes the cloud to glow brightly in different forms of radiation. It's similar to stirring cream into coffee. The smooth cloud becomes stretched into long streams and spirals, gradually disappearing as it is pulled closer and closer to the black hole. Astronomers once observed a dramatic event near the center of our galaxy, when Sagittarius A star began interacting with a large gas cloud. This cloud, known as G2, drifted dangerously close to the Milky Way's central black hole. The cloud itself was enormous, many times larger than our entire solar system. As it moved towards Sagittarius A star, the black hole's gravity began pulling and stretching the cloud into a long, thin shape. Imagine pulling apart a cotton ball until it becomes a stretched strand. Something similar happened to the gas cloud. As the cloud approached the black hole, parts of it were torn apart and heated by the extreme environment. Some of the gas was eventually pulled inward, feeding the black hole. Events like this help astronomers understand how black holes grow and how matter behaves in the intense gravity near the center of our galaxy. When the gas cloud passed close to Sagittarius A star, astronomers detected a sudden increase in infrared radiation coming from the region around the black hole. Infrared light is a type of energy that lies just beyond the red end of the visible spectrum. Humans cannot see it with their eyes, but special telescopes can detect it. As the gas cloud was stretched and heated by the black hole's gravity, the material began glowing strongly in infrared light. The heating happened because the gas was being compressed and moving at very high speeds as it spiraled inward. You can imagine rubbing your hands together quickly. The faster you rub them, the warmer they become from friction. Something similar happens when gas particles collide near a black hole. This bright infrared signal gave astronomers an important clue that the cloud was interacting with the black hole's powerful environment. The first serious mathematical description of a black hole appeared in 1916, only a year after Albert Einstein introduced his theory of general relativity. A German physicist named Karl Schwarzschild found a solution to Einstein's equations that described how gravity behaves around a very compact, massive object. At the time, Schwarzschild was serving in World War I and working under extremely difficult conditions. Yet he managed to solve one of the most important problems in theoretical physics. His solution showed that if enough mass were squeezed into a small enough space, gravity would become so strong that not even light could escape. This idea was shocking at the time. Many scientists thought such an object might only exist in mathematics. But decades later, astronomers began finding real evidence that objects matching Schwarzschild's prediction, what we now call black holes, actually exist in the universe. Karl Schwarzschild's work led to an important concept called the Schwarzschild radius. This radius defines the size of the boundary where gravity becomes so strong that nothing, not even light, can escape. In other words, it describes the size of a black hole's event horizon. If the black hole is not spinning, the idea is surprisingly simple. If you compress any object into a space smaller than its Schwarzschild radius, it would become a black hole. For example, if Earth were somehow squeezed down to about 9 millimeters across, roughly the size of a marble, its gravity would become strong enough to trap light. That same principle applies to stars. If a massive star collapses small enough, it crosses its Schwarzschild radius and forms a black hole. This concept helped scientists understand that black holes are not magical objects. They follow precise mathematical rules, predicted by Einstein's theory of gravity. For a black hole that is not spinning, the Schwarzschild radius defines the exact size of its event horizon. This means the event horizon forms a perfect spherical boundary around the black hole. Inside this boundary, gravity becomes so overwhelming that escape is impossible. Outside the boundary, objects can still move freely through space if they stay far enough away. You can imagine the event horizon like an invisible bubble surrounding the black hole. Nothing physically marks the edge. You would not see a wall or surface, but crossing that boundary changes everything. For a non-spinning black hole, the event horizon is perfectly smooth and round, like a dark sphere floating in space. In reality, many black holes rotate, which can slightly distort the shape of the event horizon. But the Schwarzschild radius remains the simplest way scientists calculate where the point of no return begins. If the entire mass of Earth were somehow compressed into a black hole, the resulting object would be unbelievably small. Its event horizon would measure only about 9 millimeters across, roughly the size of a marble or a small grape. That means the mass of our entire planet, every mountain, ocean, building, and person, would be squeezed into something smaller than a coin. Despite its tiny size, the gravity near that marble-sized black hole would be extremely powerful. Anything passing very close to it would be pulled inward immediately. However, from a distance, its gravity would behave just like Earth's gravity does today. The Moon, for example, would continue orbiting normally if it stayed far enough away. This shows how black holes are not necessarily huge in size. Their incredible power comes from packing enormous amounts of mass into an extremely tiny space. If the Sun were somehow compressed into a black hole, the event horizon would be only about 3 kilometers across. That is roughly the length of a short highway drive through a small town. This is astonishing when you consider how huge the Sun currently is. The Sun's diameter today is about 1.4 million kilometers, large enough that about 1.3 million Earths could fit inside it. Turning the Sun into a black hole would mean squeezing all that mass down into a space about the size of a city. Even more surprising, the gravity affecting the planets would stay almost exactly the same. Earth would still orbit normally at the same distance. The only difference is that the Sun would no longer shine. Our solar system would suddenly become dark and frozen, orbiting an invisible black hole instead of a glowing star. The size of a black hole's event horizon depends directly on its mass. The more mass a black hole contains, the larger its event horizon becomes. This means bigger black holes create a larger region where escape is impossible. For example, a black hole with the mass of our Sun would have an event horizon about 3 kilometers wide. But if a black hole had 10 times the Sun's mass, its event horizon would grow to about 30 kilometers across. Supermassive black holes take this idea to incredible scales. A black hole with millions or billions of solar masses can have an event horizon wider than our entire solar system. Imagine a dark sphere large enough to swallow the orbits of multiple planets. Even though these black holes are enormous, their size still follows a simple rule. More mass always means a larger event horizon. Black holes have gravity so powerful that they can bend the path of light traveling nearby. Normally, light moves in straight lines through space, but when it passes close to a massive object, gravity can curve the space around it, causing the light to change direction. This effect becomes extremely strong near a black hole. You can imagine it like rolling a marble across a stretched rubber sheet. If there is a heavy object sitting on the sheet, the marble's path curves as it passes by the dip. Light behaves in a similar way when space-time is curved by gravity. Near a black hole, this bending can become so dramatic that light from stars behind the black hole can curve around it and reach us from unexpected directions. Because of this, a black hole can act like a strange cosmic lens, distorting and magnifying the light of objects far behind it. When a black hole bends the path of light, the effect is called gravitational lensing. The name comes from the way gravity acts like a giant cosmic lens, similar to the glass lenses used in telescopes or magnifying glasses. When light from a distant star or galaxy passes near a black hole, the intense gravity curves the light's path. Instead of traveling straight toward Earth, the light may bend around the black hole before reaching us. This bending can create strange visual effects. A single distant object might appear stretched, distorted, or even duplicated in the sky. In some cases, the light forms a glowing ring around the black hole, called an Einstein ring. It's similar to looking through the curved glass of a magnifying lens that bends and stretches the image behind it. Except in this case, the lens is not glass, it's gravity itself. Around a black hole there exists a strange region called the photon sphere, where light itself can orbit the black hole. Normally, light travels in straight lines through space at incredible speed, about 300,000 kilometers per second. But near a black hole, gravity can bend light so strongly that it forces light into curved paths. Inside the photon sphere, the pull of gravity is just strong enough that light can travel in a circular orbit around the black hole. You can imagine throwing a ball around a planet so fast that it keeps falling toward the planet but never hits the ground. In theory, it keeps circling forever. Light behaves in a similar way at the photon sphere. However, these orbits are extremely unstable. Even the tiniest disturbance can cause the light to either escape into space or spiral into the black hole. Inside the photon sphere, light particles called photons can travel in circular paths around a black hole. However, these paths are extremely unstable. Even the smallest disturbance can change what happens to the light. Imagine balancing a marble on the very top of a round hill. If the marble sits perfectly still, it could remain there for a moment. But the tiniest push will cause it to roll off one side or the other. The photon sphere works in a similar way. Light moving in this region is balanced between escaping the black hole's gravity and falling inward. A tiny change in direction can decide its fate. If the light moves slightly outward, it can escape into space. But if it shifts slightly inward, it will spiral down and disappear beyond the event horizon. This delicate balance makes the photon sphere one of the most unusual regions around a black hole. Some black holes spin so fast that their shape becomes slightly flattened rather than perfectly round. Normally, a non-spinning black hole has a spherical event horizon, like a perfectly shaped ball, but when a black hole rotates extremely rapidly, its spin causes the event horizon to bulge outward around the middle. This effect is similar to what happens with planets. For example, Earth is not a perfect sphere. Because our planet spins, it bulges slightly at the equator and becomes a little flattened at the poles. The faster an object spins, the more noticeable this effect becomes. The same thing happens with rapidly spinning black holes. Their event horizons stretch outward around the middle due to the intense rotation. Even though the distortion is small compared to the black hole's overall size, it shows how extreme rotation can shape one of the most powerful objects in the universe. Rotating black holes are described by a mathematical model known as the Kerr metric, named after physicist Roy Kerr, who discovered the solution in 1963. His work expanded on earlier black hole theories that only described non-spinning black holes. In reality, most black holes are expected to rotate because the stars that formed them were already spinning before they collapsed. The Kerr model shows that spinning black holes behave very differently from non-rotating ones. Their rotation twists space-time around them and creates special regions where space itself is dragged along by the spin. One of these regions is called the ergosphere, where objects cannot remain still and must move in the direction of the black hole's rotation. You can imagine standing in a powerful whirlpool where the water is moving so strongly that you are forced to spin along with the current. It might sound impossible, but in theory, energy can actually be extracted from a spinning black hole. This strange idea comes from the behavior of rotating black holes and the special region around them called the ergosphere. Inside the ergosphere, space-time is dragged around by the black hole's rotation so strongly that nothing can remain still. Everything is forced to move in the direction of the spin. Scientists realized that if an object entered this region and then split into two pieces, one piece could fall into the black hole, while the other escapes with extra energy. It's similar to throwing a ball into a fast-moving whirlpool and having part of it slingshot outward with more speed than it had before. This theoretical process is called the Penrose process, and it shows that a spinning black hole actually stores enormous amounts of rotational energy. The idea of extracting energy from a rotating black hole is known as the Penrose process, named after physicist Roger Penrose, who proposed it in 1969. His idea showed that the spinning motion of a black hole contains enormous stored energy. The process takes place inside the ergosphere, a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. In theory, an object entering this region could split into two parts. One part would fall into the black hole, while the other escapes with more energy than the original object had. It's similar to using a moving walkway at an airport. If you run along the walkway and then jump off, you can leave with extra speed. In the same way, the Penrose process allows escaping material to gain energy from the black hole's rotation. It might sound surprising, but black holes may not last forever. Scientists believe they can very slowly evaporate over time. This idea comes from a strange prediction in modern physics that combines gravity with quantum theory. Even though nothing can escape from inside the event horizon, space around a black hole is not completely empty. Tiny quantum effects constantly create pairs of particles that appear and disappear very quickly. Near a black hole, something unusual can happen. One particle from the pair may fall into the black hole while the other escapes into space. When this happens, the escaping particle carries away a tiny amount of energy. Since energy and mass are connected, the black hole loses a tiny bit of its mass each time this occurs. This process is incredibly slow, but over extremely long timescales, it could cause a black hole to gradually shrink. The idea that black holes might slowly lose mass was proposed by physicist Stephen Hawking in the 1970s. Before his work, most scientists believed black holes could only grow larger by swallowing matter. Hawking used principles from quantum physics to study what happens near the edge of a black hole. He discovered that tiny particle effects in empty space could cause black holes to release a very small amount of energy. This radiation is now called Hawking radiation. The discovery shocked the scientific world because it showed that black holes are not completely black. Instead, they can slowly leak energy over time. Imagine a massive block of ice that appears solid and permanent, but very slowly melts away drop by drop. Hawking suggested that black holes may behave in a similar way, gradually shrinking as they lose energy to space. According to Stephen Hawking's theory, black holes emit a very tiny amount of energy called Hawking radiation. This radiation comes from strange quantum effects happening just outside the event horizon. In empty space, pairs of particles constantly appear and disappear for extremely short moments. Normally, these pairs cancel each other out almost instantly. But near a black hole, gravity can separate them before they disappear. One particle may fall into the black hole while the other escapes into space. The escaping particle becomes real radiation that travels away from the black hole. You can imagine it like two people holding hands while standing near the edge of a cliff. If one slips and falls while the other is pulled away, the pair becomes separated. Each time this happens, the black hole loses a tiny bit of energy and mass, slowly shrinking over incredibly long periods of time. Because of Hawking radiation, scientists believe black holes may eventually disappear completely. Each tiny burst of radiation carries away a small amount of the black hole's energy. Since energy and mass are connected, this slowly reduces the black hole's total mass. At first, the process happens incredibly slowly. The black hole loses only tiny amounts of mass over extremely long periods of time. But as the black hole gets smaller, the radiation becomes stronger. Eventually, the black hole may shrink faster and faster. You can imagine a block of ice melting under warm sunlight. At first, the melting is slow, but as the ice becomes smaller, it disappears more quickly. In the far future of the universe, this process could cause black holes to evaporate completely, leaving behind only a burst of radiation where one of the most powerful objects once existed. Although black holes may eventually evaporate, the process takes an unbelievably long time. A black hole with the mass of our Sun would need around 10 to the power 67 years to completely disappear through Hawking radiation. To understand how long that is, consider the current age of the universe. Scientists estimate the universe is about 13.8 billion years old. Compared to that, 10 to the power of 67 years is so large that the universe would need to exist billions upon billions of times longer than it already has. It's like comparing 1 second to a time longer than the entire history of Earth repeated countless times. This means that any black holes we observe today will likely remain for an incredibly long future. Long after stars burn out and galaxies grow dark, black holes may still exist quietly in the universe. They could become some of the last massive objects remaining in the far future of the cosmos. Black holes can create powerful shockwaves in the gas surrounding them. When matter falls toward a black hole, It often moves at extremely high speeds. As this fast-moving material collides with other gas in space, it can produce sudden bursts of pressure that travel outward like waves. You can picture this like the shock wave created when a jet breaks the sound barrier. The aircraft pushes through the air so quickly that it sends a strong pressure wave outward. Something similar happens near black holes, but on a far larger scale. The gas near an active black hole may be heated, compressed, and pushed outward by these shock waves. In some galaxies, the waves travel thousands of light years away from the black hole. These cosmic shock waves can affect how gas moves through the galaxy, and may even influence where new stars can form. Some black holes are relatively quiet, but others become incredibly active and energetic. These black holes feed on large amounts of gas, dust, and sometimes even stars that drift too close. When a huge supply of material falls toward the black hole, the surrounding accretion disk becomes extremely bright and chaotic. Gas particles move at tremendous speeds, colliding and heating up to millions of degrees. The energy released can be enormous. Radiation, jets, and powerful winds can blast outward from the region around the black hole. Imagine a calm campfire suddenly turning into a roaring furnace when more fuel is added. The same thing happens when a black hole receives a large supply of matter. These active black holes can shine across vast distances in the universe, allowing astronomers to detect them even from billions of light years away. When a supermassive black hole at the center of a galaxy becomes extremely active, the region around it is called an active galactic nucleus, often shortened to AGN. The word nucleus simply means the central core of the galaxy. In these systems, huge amounts of gas and dust are falling toward the black hole. As the material spirals inward, it forms a blazing accretion disk that shines with tremendous energy. The light and radiation from an active galactic nucleus can be so powerful that it spreads across the entire galaxy. In some cases, this central region shines brighter than billions of surrounding stars. Imagine a tiny but incredibly bright engine placed at the center of a vast city. Even though the engine itself is small, the energy it releases lights up the entire area around it. Active galactic nuclei are among the brightest objects astronomers observe in the universe. Active black holes can produce radiation across the entire electromagnetic spectrum. This means they release energy in many different forms of light, including radio waves, infrared, visible light, ultraviolet light, X-rays, and even powerful gamma rays. The reason for this wide range of radiation comes from the extreme environment around the black hole. Gas in the accretion disk becomes incredibly hot, often reaching millions of degrees. At the same time, particles are accelerated to enormous speeds by magnetic fields and powerful jets. Different processes in this chaotic region produce different kinds of radiation. For example, cooler gas may glow in infrared light, while extremely hot gas emits X-rays. High-speed particles in jets can produce radio waves and gamma rays. It's like a giant cosmic light show where nearly every form of energy in the universe is being produced at once. Some jets launched from black holes travel at speeds very close to the speed of light. The speed of light is about 300,000 kilometers per second, which is fast enough to circle the entire Earth more than 7 times in a single second. Particles in these jets can reach a large fraction of that incredible speed. Once accelerated, they blast outward from the regions near the black hole in narrow beams that stretch across huge distances in space. These jets are powered by the extreme environment around the black hole. Magnetic fields, spinning matter, and the black hole's rotation all work together to launch streams of high-energy particles outward. Imagine a gigantic cosmic fire hose shooting matter across space at nearly the fastest speed possible in the universe. Even though the black hole itself is dark, these powerful jets can shine brightly and be detected from millions or even billions of light years away. Black holes can strongly influence how stars move near the center of a galaxy. Their powerful gravity acts like an invisible anchor that pulls nearby stars into fast, curved paths around them. Near the center of the Milky Way, some stars travel at incredible speeds while orbiting the hidden black hole Sagittarius A star. These stars are not moving randomly. Instead, they follow precise elliptical paths, much like planets orbiting the Sun. However, the speeds involved are far greater. Some stars near the galactic center move thousands of kilometers per second. To imagine this, think about Earth orbiting the Sun at about 30 kilometers per second. Stars near the central black hole move hundreds of times faster than that. By carefully measuring these rapid motions, astronomers can calculate the mass of the invisible object pulling on them, revealing the presence of the black hole. Astronomers confirmed the existence of Sagittarius A star by carefully observing the motion of stars near the center of the Milky Way. Using powerful telescopes, scientists tracked these stars for many years and noticed something remarkable. Several stars were moving in extremely tight and fast orbits around a point where no visible object could be seen. The speeds were astonishing. Some stars were racing through space at thousands of kilometers per second. By studying these orbits, scientists calculated that an object about 4 million times the mass of the Sun must be sitting at the center. Yet nothing bright or visible was there. The only explanation that fit the observations was a supermassive black hole. It's similar to seeing leaves spinning quickly around an invisible drain in water. Even if you cannot see the drain itself, the motion of the leaves reveals its hidden presence. One of the most famous stars near the center of the Milky Way completes a full orbit around Sagittarius A star in only 16 years. This star, often called S2, travels on a long elliptical path that swings it very close to the central black hole. To understand how fast that is, consider the planets in our solar system. Earth takes 1 year to orbit the Sun, while Neptune, the farthest major planet, takes about 165 years to complete a single orbit. Yet this star circles a black hole millions of times heavier than the Sun in just 16 years. When S2 gets closest to the black hole, it speeds up dramatically, reaching around 7,600 kilometers per second. That's more than 25 million kilometers per hour. Observing this star's motion has provided some of the strongest evidence that a supermassive black hole truly sits at the center of our galaxy. The motion of stars like S2 helped astronomers uncover the enormous hidden mass at the center of the Milky Way. By tracking how these stars move over many years, scientists can use the laws of gravity to calculate what must be pulling on them. It works in a similar way to watching planets orbit the Sun. From the speed and shape of their orbits, scientists can determine the Sun's mass. When astronomers studied the stars near the galactic center, they discovered something incredible. All the stars were orbiting a tiny region of space that contained about 4 million times the mass of the Sun. Yet that region was extremely small, much smaller than our solar system. No cluster of normal stars could fit that much mass into such a tiny space. The only object capable of doing this is a supermassive black hole hidden at the center of our galaxy. Some black holes may have formed in a very different way than those created by dying stars. In the early universe, enormous clouds of gas may have collapsed directly under their own gravity, forming black holes without first becoming stars. These gas clouds could have been incredibly massive, containing millions of times the mass of the Sun. When gravity pulled the cloud inward, the material may have collapsed so quickly that it skipped the normal process of star formation. Instead of forming many smaller stars, the entire cloud could have compressed into a single massive object, eventually becoming a black hole. You can imagine a huge storm cloud collapsing into a powerful whirlpool, rather than breaking into many smaller droplets. Scientists think this process might explain how some supermassive black holes appeared so early in the universe, long before galaxies had enough time to grow them slowly through normal star collapses. The giant black holes found at the centers of galaxies likely did not start out enormous. Scientists believe they may have begun as smaller seed black holes that formed in the early universe and then grew over time. These seeds may have formed from the collapse of massive gas clouds or from the deaths of the first generations of giant stars. Once the initial black hole existed, gravity allowed it to begin pulling in nearby gas, dust, and even entire stars. As matter fell into the black hole, its mass increased. Over millions and billions of years, this feeding process allowed the black hole to grow larger and larger. It's similar to planting a tiny seed that slowly grows into a massive tree. By continuously gathering matter and sometimes merging with other black holes, these early seeds could eventually become the supermassive black holes that anchor the centers of galaxies today. Some black holes formed very early in the history of the universe, when the cosmos was still young and chaotic. Shortly after the Big Bang, the universe contained huge clouds of hot gas and the first generations of massive stars. Many of these early stars were far larger than most stars we see today. Some may have been hundreds of times the mass of the Sun. Because they were so massive, they burned their fuel quickly and collapsed after relatively short lifetimes. When these giant stars died, their cores could collapse into black holes. Since this happened when the universe was still very young, these early black holes had a long time to grow by pulling in gas, dust, and even merging with other black holes. Over billions of years, some of these early objects may have grown into the supermassive black holes found in galaxies today. Astronomers have discovered extremely bright quasars that existed when the universe was less than 1 billion years old. Considering that the universe today is about 13.8 billion years old, this means these objects appeared very early in cosmic history. Quasars are powered by supermassive black holes, feeding on huge amounts of gas. The surprising part is how quickly these black holes must have grown. In less than 1 billion years, some of them already reached masses of billions of times the Sun's mass. To imagine this growth, it's like planting a tiny seed and somehow having it grow into a massive forest tree in just a few years. This discovery puzzled astronomers because normal black hole growth should take much longer. The existence of these early quasars suggests that black holes may have formed earlier or grown faster than scientists originally expected. The black holes powering early quasars are incredibly massive. Some of them already reached billions of times the mass of the Sun when the universe was less than 1 billion years old. This is surprising because growing a black hole to that size normally takes a very long time. A black hole must continuously pull in gas, dust, and sometimes even stars to increase its mass. Imagine trying to grow a small sapling into a giant tree in just a short time. It would need an enormous supply of nutrients and perfect conditions to grow that quickly. In the same way, these early black holes must have been feeding at extremely high rates. Astronomers are still studying how this happened. The discovery suggests that the early universe may have provided special conditions that allowed black holes to grow much faster than expected. One of the biggest mysteries in astronomy today is how supermassive black holes grew so quickly in the early universe. Scientists know that black holes increase their mass by pulling in gas, dust, and sometimes merging with other black holes. But even with steady feeding, growing to billions of solar masses should take a very long time. Yet, observations show that some black holes had already reached these enormous sizes when the universe was less than 1 billion years old. To picture the puzzle, imagine trying to grow a city from a single house in just a few years. Even with constant construction, the timeline seems too short. Because of this, astronomers are exploring different explanations. Perhaps the first black holes started much larger than expected. Or maybe they were able to feed on huge amounts of gas very rapidly in the young universe. The answer is still being investigated. One way black holes may grow larger is by merging with other black holes. When two galaxies collide, the massive black holes at their centers can eventually move toward each other due to gravity. At first, the black holes may orbit one another from a great distance. Over time, Their orbit slowly shrinks as they lose energy through gravitational waves and interactions with nearby stars and gas. Eventually, the two black holes spiral closer and closer together until they finally collide and merge into a single larger black hole. You can imagine two whirlpools in water slowly drifting together until they combine into one stronger vortex. Each merger adds the mass of both black holes into one object. If this process happens many times over billions of years, a black hole can grow enormously large, helping explain how some become supermassive giants at the centers of galaxies. When galaxies collide, their central black holes can eventually be brought closer together by gravity. Galaxies are enormous systems containing billions of stars, gas clouds, and dark matter, and they constantly move through space. Over long periods of time, some galaxies drift close enough to interact and merge. When two galaxies begin merging, their stars usually pass by each other without crashing, because the distances between stars are huge. However, the supermassive black holes at the centers of those galaxies feel each other's gravitational pull. As the galaxies combine, the black holes slowly move toward the new shared center. Over millions of years, interactions with nearby stars and gas act like cosmic friction, gradually pulling the two black holes closer together. Eventually, they can form a pair of orbiting black holes, setting the stage for a future merger that releases powerful gravitational waves. Before two black holes finally merge, they can spend a long time orbiting each other as a pair, forming what astronomers call a binary black hole system. In this stage, the two black holes circle around their shared center of gravity, much like two dancers spinning around each other. These orbits can last for millions or even billions of years, depending on their distance and mass. As they continue orbiting, the black holes gradually move closer together. This happens because their motion produces gravitational waves which carry energy away from the system. You can imagine two spinning ice skaters holding hands. As they pull closer together, they spin faster and faster. The same thing happens with binary black holes. As their distance shrinks, their orbital speed increases dramatically until they eventually collide and merge into a single larger black hole. When two black holes orbit each other, their motion slowly changes over time. As they circle together, they produce gravitational waves, which are ripples traveling through space-time. These waves carry energy away from the system. Because energy is being lost, the black holes cannot keep the same orbit forever. Their paths gradually shrink, causing them to spiral closer together. You can imagine two spinning tops connected by an invisible thread. If energy slowly drains from the system, the tops would move closer and spin faster. The same thing happens with binary black holes. At first, their orbit may be wide and slow, but as gravitational waves carry energy away, the orbit becomes smaller and the speed increases. Eventually, the black holes move so close that they collide and merge in a final burst of gravitational waves, sending powerful ripples across the universe. Some black holes create enormous bubbles of hot gas inside galaxy clusters. A galaxy cluster is a huge collection of galaxies held together by gravity, often containing hundreds or even thousands of galaxies. At the center of some clusters sits a powerful supermassive black hole. When this black hole becomes active, it can launch strong jets of energy outward. These jets push into the surrounding hot gas that fills the cluster. As the jets blast through the gas, they carve out massive cavities, forming bubble-like regions where the gas has been pushed aside. These bubbles can be hundreds of thousands of light years wide, far larger than entire galaxies. You can imagine blowing air into thick foam and watching large pockets form inside it. In a similar way, black hole jets inflate giant bubbles within the hot gas of galaxy clusters. The enormous bubbles created by black hole jets can actually control how many stars form in a galaxy cluster. When jets from a supermassive black hole push into the surrounding gas, they heat the gas and stir it up. Normally, cool gas can slowly collapse under gravity and form new stars. But when the gas becomes too hot, it spreads out and becomes harder to compress. You can imagine trying to form snowballs with warm, fluffy snow compared to cold, packed snow. When the snow is too warm, it refuses to stick together. Something similar happens with gas in galaxy clusters. The energy released by the black hole prevents the gas from cooling too much. Because of this, the black hole acts like a giant cosmic regulator, controlling how quickly new stars can form in the surrounding galaxies. Not all black holes are dramatic or violent. Many of them consume matter quietly, without producing bright explosions or powerful jets. These calmer black holes slowly pull in small amounts of gas and dust from their surroundings. When the supply of nearby material is limited, the accretion disk around the black hole may remain faint and relatively stable. The gas still spirals inward and heats up, but the energy released is much lower compared to active black holes. You can think of it like a small campfire slowly burning a few pieces of wood instead of a raging bonfire. Our own galaxy's central black hole, Sagittarius A star, is currently in this quieter state. It is not feeding on large amounts of matter right now, which is why the center of the Milky Way appears relatively calm compared to some extremely bright galaxies. While some black holes feed quietly, others can suddenly become extremely violent and bright. When a large amount of gas, dust, or even a star suddenly falls toward the black hole, the environment around it can flare up dramatically. As the material spirals inward, it heats up to millions of degrees and releases powerful bursts of radiation. These flares can shine brightly across many forms of light, including X-rays and visible light. Imagine a calm fire that suddenly erupts when a large pile of fuel is thrown onto it. The flames surge upward, burning much brighter and hotter. Something similar happens near a black hole when fresh material suddenly arrives. These violent outbursts can last from a few hours to many years, depending on how much material is being consumed, making the black hole temporarily one of the brightest objects in its galaxy. Even though black holes are famous for swallowing matter, they don't actually keep everything that falls toward them. In many cases, some of the incoming material is ejected back into space, instead of crossing the event horizon. As gas spirals into the accretion disk around a black hole, it becomes extremely hot and chaotic. Powerful magnetic fields and fast rotation can redirect some of this material away from the black hole. The result is streams of particles being blasted outward in the form of jets or strong winds. You can imagine pouring water down a drain, while some of the splashing water shoots back upward due to turbulence. A similar process happens near black holes, though on a far larger and more energetic scale. This means black holes are not just cosmic consumers, they can also act as powerful engines that push matter back into the surrounding galaxy. The powerful outflows and jets produced by black holes can actually shape the structure of their surrounding galaxies. When matter is blasted outward at high speeds, it pushes on the gas and dust spread throughout the galaxy. This movement can change how gas flows through the galaxy and where new stars are able to form. Imagine a powerful leaf blower pushing leaves across a yard. The airflow changes where the leaves gather and how they spread out. In a similar way, black hole outflows can move enormous clouds of gas across vast regions of space. Some of these outflows travel thousands of light years away from the black hole. Because gas is the main ingredient needed to create stars, the movement of this gas can influence where future stars are born, allowing black holes to quietly shape the evolution of their entire galaxy. Some black holes exist in binary star systems, where they share a gravitational relationship with a normal star. In these systems, the black hole and the star orbit around a common center, similar to how two dancers spin around each other. At first, the black hole may simply orbit quietly beside its companion star, but over time, its strong gravity can begin pulling gas from the star's outer layers. Stars are made mostly of hot gas, and if the star drifts close enough, the black hole's gravity can stretch and pull that gas away. You can imagine a powerful vacuum, slowly pulling steam from a boiling pot nearby. The stolen gas does not fall straight into the black hole. Instead, it spirals inward, forming a bright accretion disk that heats up and glows strongly. This glowing gas often reveals the hidden black hole to astronomers. In a binary system, a black hole can slowly pull gas away from its companion star. This happens because the black hole's gravity can overpower the outer layers of the nearby star. Stars are not solid objects like planets. They are giant spheres of hot gas. When a black hole sits close enough, its gravity can stretch the star and pull streams of gas toward itself. You can imagine holding a drop of thick syrup between two fingers and slowly pulling them apart. The syrup stretches into a long, thin strand before separating. Something similar happens in space. Gas from the star stretches into a long stream and flows toward the black hole. This stolen gas begins spiraling around the black hole, forming a hot accretion disk that glows brightly. The process can continue for thousands or even millions of years as the black hole steadily feeds. When gas from a companion star spirals toward a black hole, it does not fall straight in. Instead, it forms a spinning accretion disk around the black hole. Inside this disk, the gas moves incredibly fast as it circles closer and closer to the event horizon. As the gas particles move and collide with each other, they create intense friction. This friction heats the gas to extremely high temperatures. The temperatures can rise to millions of degrees, which is far hotter than the surface of most stars. At these temperatures, the gas begins to glow brightly and release powerful radiation. You can imagine rubbing your hands together quickly. The faster you rub them, the warmer they become. Now imagine trillions of particles doing something similar at enormous speeds. This intense heating makes the region around the black hole shine brightly, even though the black hole itself remains completely dark. When gas near a black hole heats up to millions of degrees, it begins to release powerful energy known as X-rays. X-rays are a very energetic form of light that humans cannot see with their eyes, but special space telescopes can detect them. In binary systems, where a black hole pulls gas from a nearby star, the accretion disk becomes extremely hot. As the gas spirals inward and gets squeezed by gravity, it glows strongly in X-rays. To imagine how energetic this is, think about how hot a stove burner becomes when turned to its highest setting. Now multiply that heat millions of times. These intense X-ray signals are one of the main ways astronomers discover hidden black holes. Even though the black hole itself remains invisible, the glowing X-ray radiation from the surrounding gas acts like a bright beacon in space. When a black hole pulls gas from a nearby companion star and produces strong X-rays, the system is known as an X-ray binary. The word binary means there are two objects involved, the black hole and the normal star. In these systems, the star and the black hole orbit each other due to gravity. As gas from the star flows toward the black hole, it forms a hot accretion disk. The intense heat and motion in the disk cause it to release powerful X-rays into space. These X-rays can travel across vast distances, allowing astronomers to detect the system even if the black hole itself cannot be seen. You can think of it like a lighthouse beam shining from the middle of the ocean. The lighthouse reveals the location of the island even though the island itself might be hidden in the dark. X-ray binaries are one of the clearest signs that a black hole is present. Some black holes spin incredibly fast, completing hundreds of rotations every single second. This rapid spin usually happens when a black hole pulls in large amounts of gas from a nearby star or accretion disk. As the material spirals inward, it transfers angular momentum to the black hole, causing its rotation to speed up. Over time, the black hole can spin faster and faster. To imagine this speed, think about a household blender spinning at high power. Now picture something thousands of times heavier than our sun rotating hundreds of times every second. Even though the black hole itself may only be a few dozen kilometers across, its edge can move at astonishing speeds. This extreme rotation has powerful effects on the surrounding space. It can twist space-time, strengthen magnetic fields, and help launch some of the fastest jets of particles in the universe. The fastest spinning black holes rotate so quickly that the edge of their event horizon moves at a large fraction of the speed of light. The speed of light is about 300,000 kilometers per second, which is fast enough to circle Earth more than 7 times in a single second. Near these extreme black holes, space itself is dragged around by the spin. The rotation becomes so powerful that the outer region of the black hole effectively moves through space-time at incredible speed. To picture this, imagine a carousel spinning faster and faster. The horses near the center move slowly, but the ones at the edge move much faster. Something similar happens with spinning black holes. The closer you get to the edge of the event horizon, the faster the motion becomes. These extreme speeds help power energetic phenomena like jets and intense radiation around rapidly spinning black holes. In some cases, the accretion disk around a black hole can become brighter than the entire galaxy that contains it. This happens when huge amounts of gas and dust are falling toward a supermassive black hole at the center of a galaxy. As the material spirals inward, it becomes compressed, heated, and accelerated to enormous speeds. The collisions and friction between particles release tremendous amounts of energy. Even though the glowing disk may only be about the size of our solar system, it can produce more light than hundreds of billions of stars spread across a galaxy. To imagine this contrast, picture a tiny light bulb shining brighter than all the streetlights in an entire city. These incredibly bright systems are often observed as quasars, which can be seen from billions of light years away, making them some of the most luminous objects in the universe. Some black holes are extremely difficult to detect because they are hidden behind thick clouds of dust and gas. In many galaxies, large amounts of dust gather near the center, surrounding the supermassive black hole. This dust can block visible light, making the central region appear dark or completely hidden when observed with ordinary telescopes. You can imagine trying to look at a bright lamp through a thick fog. The light becomes faint or disappears from view, even though the lamp is still shining behind the fog. Something similar happens with dusty galaxies. The black hole and its glowing accretion disk may be extremely bright, but the surrounding dust absorbs or scatters the visible light. Because of this, many active black holes remained hidden for a long time until astronomers began using telescopes that can observe other forms of radiation beyond visible light. Even when thick dust hides a black hole from normal telescopes, scientists can still find it using infrared telescopes. Infrared light has longer wavelengths than visible light, which allows it to pass through dust clouds more easily. You can think of this like using special night vision goggles. Even in darkness or fog, these devices can detect heat and reveal objects that would normally remain invisible. In a similar way, infrared telescopes can detect the warm glow of dust heated by an active black hole. When gas and dust spiral into the black hole, the surrounding material becomes extremely hot and begins to radiate infrared energy. Space telescopes designed to observe infrared light can see through the dusty veil and detect these hidden signals. Thanks to infrared observations, astronomers have discovered many previously hidden black holes that were completely invisible in ordinary visible light. Black holes may help create and strengthen cosmic magnetic fields that stretch across enormous regions of space. Near an active black hole, gas in the accretion disk moves extremely fast and becomes highly energized. When charged particles in this hot gas move rapidly, they can generate powerful magnetic fields. These magnetic fields can twist, stretch, and organize the material around the black hole. You can imagine stirring metal filings with a magnet. As the magnet moves, the filings arrange themselves into patterns that reveal the magnetic forces. Something similar happens near black holes. The spinning disk of hot gas acts like a giant cosmic generator, producing magnetic fields that guide particles into jets and outflows. These magnetic forces can extend far beyond the black hole itself, helping shape the movement of matter across vast distances in space. The powerful jets launched from black holes do more than shoot particles through space. They also carry enormous amounts of magnetic energy across vast distances in the universe. These jets are guided and shaped by strong magnetic fields created near the black hole's accretion disk. As charged particles race along these magnetic lines, the jets become tightly focused beams that travel outward at incredible speeds. You can imagine electricity flowing through a wire. The electric current follows the path created by the wire, guiding the energy in a specific direction. In a similar way, magnetic fields act like invisible rails that guide particles in black hole jets. As the jets extend into space, they transport magnetic energy far from the black hole, sometimes influencing gas clouds and even entire regions of galaxies thousands or millions of light years away. Some black hole jets grow to astonishing sizes, stretching millions of light years into space. A single light year is the distance light travels in 1 year, about 9.5 trillion kilometers. When jets extend for millions of light years, they become some of the largest structures connected to a single object in the universe. These jets begin near the black hole's accretion disk, where magnetic fields and fast-moving particles launch narrow beams outward. The particles travel at speeds close to the speed of light, allowing the jets to push far beyond the galaxy that produced them. Imagine a narrow beam of water shooting from a fire hose and continuing far across a field. Now scale that up to cosmic distances, thousands of times larger than entire galaxies. These massive jets can influence gas clouds far away, sometimes heating them or pushing them aside as they travel through intergalactic space. Black holes can influence the temperature of enormous galaxy clusters. A galaxy cluster is a massive collection of galaxies held together by gravity, often containing hundreds or even thousands of galaxies, along with huge amounts of hot gas. At the center of many clusters sits a powerful supermassive black hole. When this black hole becomes active, it releases energy through jets, radiation, and powerful outflows. This energy spreads through the surrounding gas and can heat it up dramatically. The gas in galaxy clusters is already extremely hot, often reaching tens of millions of degrees. But the black hole's energy can keep it from cooling down. You can imagine a giant heater placed in the middle of a large room. Even though the room is huge, the heater can still affect the temperature of the air. In a similar way, black holes can regulate the temperature of gas across vast regions of a galaxy cluster. Some galaxy clusters contain giant empty cavities carved out by jets from supermassive black holes. These cavities form when powerful jets blast outward from the center of a galaxy and push away the surrounding hot gas. The jets act like enormous cosmic drills, forcing their way through the gas that fills the cluster. As they push the gas aside, they leave behind bubble-like regions where the gas is much thinner. These cavities can be hundreds of thousands of light years across, which means they can be far larger than entire galaxies. You can imagine blowing bubbles in thick foam. As the air pushes outward, it creates empty pockets inside the foam. Something similar happens when black hole jets inflate cavities in galaxy clusters. Astronomers detect these giant bubbles using X-ray telescopes, which reveal where the hot gas has been pushed away. The gravity of extremely massive black holes can influence the motion of nearby galaxies, especially in dense regions of space, such as galaxy clusters. When a supermassive black hole sits at the center of a massive galaxy, its gravitational pull contributes to the overall gravitational balance of the region. Although the black hole itself is small compared to the size of a galaxy, its mass can be enormous, sometimes billions of times heavier than the Sun. Because of this, The black hole helps shape how stars, gas, and even nearby galaxies move within the cluster's gravitational environment. Imagine a heavy weight placed in the center of a stretched sheet. Objects on the sheet will naturally move along curved paths around the weight. In a similar way, the mass of supermassive black holes contributes to the complex gravitational dance of galaxies moving through clusters. The gravity of a supermassive black hole can strongly affect the entire central region of its galaxy, often called the galactic core. Even though the black hole itself occupies a tiny space, its enormous mass creates a powerful gravitational pull that dominates the surrounding area. Near the center of a galaxy, stars can orbit the black hole at extremely high speeds. Some stars travel thousands of kilometers per second while circling the invisible mass. You can imagine a giant merry-go-round in a playground. The closer you stand to the center, the faster you move as the platform spins. Something similar happens near a galactic black hole. Stars closer to the center move faster because they feel stronger gravity. Over millions of years, this strong gravitational influence helps organize how stars and gas move within the central region of the galaxy. After galaxies collide and merge, their central black holes do not always stay perfectly in the middle of the new galaxy. In some cases, a black hole can end up wandering through the galaxy instead of sitting at the center. This can happen because galaxy mergers are extremely chaotic events. When two galaxies combine, stars, gas, and dark matter shift around as gravity reshapes the entire system. If the central black holes of the two galaxies have not yet merged, one of them may move through the galaxy while gradually drifting towards the center over time. You can imagine pouring two swirling whirlpools together in water. At first, the centers of the whirlpools move around before finally settling into one stable location. In a similar way, black holes in newly merged galaxies can wander for millions of years before settling near the galactic center. Sometimes, a newly merged black hole can be launched away from the center of its galaxy in a dramatic event called a recoiling black hole. This happens when two black holes collide and merge, releasing enormous amounts of energy as gravitational waves. If the energy from these waves is not perfectly balanced in all directions, the newly formed black hole can receive a powerful push, almost like the recoil of a cannon firing. This sudden kick can send the black hole flying through its galaxy at incredible speeds. Imagine two ice skaters spinning together and then pushing off suddenly. One skater might shoot away across the ice, while the other remains closer to the center. A similar effect happens with recoiling black holes. The merged black hole can be knocked away from the galaxy's core, beginning a long journey through the surrounding stars and gas. Recoiling black holes can travel thousands of light years away from the center of their galaxy. After receiving a powerful gravitational kick, a light year is the distance light travels in 1 year, about 9.5 trillion kilometers. So moving thousands of light years is an enormous journey through space. After two black holes merge, the uneven release of gravitational waves can push the newly formed black hole at incredible speeds, sometimes thousands of kilometers per second. At these speeds, the black hole can move far from the galactic center before gravity slowly pulls it back. You can imagine a heavy bowling ball rolling across a large floor after being pushed strongly. It may travel a long distance before finally slowing down. In a similar way, a recoiling black hole can wander through the galaxy, carrying its enormous mass along a long path through stars and gas. Black holes can sometimes produce sudden bursts of powerful radiation that spread across space. These bursts usually happen when a large amount of matter suddenly falls toward the black hole. As gas, dust, or pieces of a star spiral into the accretion disk, they become compressed and heated to extremely high temperatures. This heating can release intense radiation in the form of X-rays, gamma rays, and other high-energy light. The bursts can be extremely bright, sometimes outshining large portions of the surrounding galaxy for a short time. You can imagine throwing a large pile of fuel into a fire. The flames suddenly surge upward, burning much brighter and hotter than before. In a similar way, when a black hole suddenly receives a large supply of matter, the surrounding disk can flare dramatically, producing powerful flashes of radiation detectable from great distances. Some of the most dramatic radiation bursts from black holes happen when a star is torn apart by the black hole's gravity. When a star drifts too close, the difference in gravitational pull between the near side and far side stretches the star until it breaks apart. This process is known as a tidal disruption event. As the star is shredded, huge streams of hot gas are pulled toward the black hole. Some of this material forms a bright accretion disk that heats up to millions of degrees. The sudden heating produces a powerful flare of radiation that can shine across the universe. You can imagine dropping a block of ice into extremely hot water. The sudden temperature change causes a dramatic reaction. In a similar way, the destruction of a star releases an intense burst of energy that astronomers can detect from far away. Not all radiation bursts from black holes come from destroyed stars. Sometimes they happen when the black hole suddenly begins pulling in a large amount of gas or dust, a process called accretion. If a dense cloud of gas drifts too close to the black hole, the material can quickly spiral inward and form a bright accretion disk. As the gas moves closer, it becomes squeezed and heated by friction and gravity. This sudden heating can release an intense burst of radiation across different forms of light, including X-rays and ultraviolet light. You can imagine pouring a large amount of fuel into an engine all at once. The engine suddenly roars louder as it burns the extra fuel. In a similar way, when a black hole suddenly receives a surge of matter, the surrounding disk becomes extremely energetic, producing a powerful flash of radiation that astronomers can observe. Black holes are one of the main sources of gravitational waves in the universe. Gravitational waves are ripples in space-time that travel outward when extremely massive objects move or collide. The most powerful waves are produced when two black holes orbit each other and eventually merge. As they spiral closer together, their motion shakes space-time itself, sending waves traveling across the universe. You can imagine dropping two heavy stones into a calm lake. The water surface begins to ripple outward in all directions. In a similar way, merging black holes create ripples that spread through the fabric of space and time. These waves move at the speed of light and can travel billions of light years before reaching Earth, even though the ripples become incredibly tiny by the time they arrive. Sensitive detectors like LIGO can measure them and reveal the distant black hole collision. As technology improves, scientists expect future observatories to detect thousands of gravitational wave signals from black holes. Right now, instruments like LIGO can already detect some of these cosmic ripples when large black holes merge. But these detectors are only the beginning. New observatories are being designed with much greater sensitivity. Some will be placed in space, where they can measure gravitational waves that are impossible to detect from Earth. One planned mission will use spacecraft separated by millions of kilometers to measure tiny distortions in space-time. You can imagine upgrading from a small microphone to an extremely powerful one that can hear whispers from miles away. With better detectors, astronomers will be able to listen to many more black hole mergers happening across the universe, revealing events that are currently too faint or distant for us to detect. Gravitational wave signals do more than confirm that black holes collide. They also help astronomers understand how black holes grow over time. Each signal carries detailed information about the objects that created it. When two black holes merge, the shape of the gravitational wave reveals their masses, speeds, and spins. By studying these signals, scientists can learn how big the original black holes were and how large the final black hole became after the collision. It's a bit like hearing the sound of two objects crashing together in the dark. From the sound alone, you might estimate how heavy the objects were and how fast they were moving. In a similar way, Gravitational waves act like cosmic recordings of black hole mergers. By collecting many of these signals, astronomers can piece together the long history of how black holes formed and grew throughout the universe. Black holes give scientists a powerful way to test Einstein's theory of relativity under extreme conditions. Einstein's theory describes how gravity works by explaining how massive objects bend space-time. Most everyday gravitational effects, like Earth orbiting the Sun, fit Einstein's predictions very well. But near a black hole, gravity becomes far more intense than anywhere else we can easily observe. This makes black holes like natural laboratories for studying gravity at its strongest. For example, astronomers have measured how stars move near the Milky Way's central black hole and compared their motion to Einstein's predictions. The results match the theory with incredible accuracy. It's similar to testing a machine by running it under extreme pressure. If it still works perfectly, it confirms the design. In the same way, black holes help scientists check whether Einstein's ideas still hold true in the most extreme environments. Black holes push the laws of physics to their absolute limits. The gravity near a black hole becomes so strong that it stretches space and slows time in ways that do not happen anywhere else we can easily observe. Near the event horizon, gravity is so intense that even light struggles to escape. Time itself can slow dramatically compared to regions far away. Imagine standing near a giant whirlpool where the water moves faster and faster the closer you get to the center. The environment becomes more extreme as you approach the middle. Black holes create a similar situation for physics. The closer something moves toward the event horizon, the more unusual the behavior of space, time, and energy becomes. Because of this, scientists study black holes to understand where our current theories may break down and where new physics might be waiting to be discovered. Some scientists think that extremely small black holes may have formed shortly after the universe began. These are called primordial black holes, meaning they formed in the earliest moments of cosmic history. In the young universe, matter was not spread evenly. Some regions may have been much denser than others. If enough mass gathered in a small area, gravity could have caused that region to collapse directly into a black hole. Unlike most black holes that form from dying stars, primordial black holes might have formed without any star at all. Some of them could have been tiny, perhaps no larger than a mountain or even an asteroid, yet containing enormous mass. It's like compressing a huge mountain into a space smaller than a city. Scientists are still searching for evidence of these ancient objects to learn whether they truly formed in the early universe. Black holes that may have formed in the early universe are known as primordial black holes. Unlike most black holes, which form when massive stars collapse, primordial black holes could have appeared shortly after the Big Bang, when the universe was extremely hot and dense. During that early time, small regions of space may have contained slightly more matter than the surrounding areas. If enough mass gathered in one tiny region, gravity could have caused it to collapse directly into a black hole. These early black holes could have formed in many different sizes. Some might have been small, while others could have been much larger. You can imagine tiny pockets of heavy material suddenly collapsing under their own weight, like small dents forming in a stretched sheet. If primordial black holes exist, they would be some of the oldest objects in the universe, formed near the very beginning of cosmic history. Some scientists think primordial black holes might help explain one of the biggest mysteries in astronomy: dark matter. Dark matter is an invisible form of matter that does not emit light, but its gravity affects how galaxies move. When astronomers observe galaxies, they find that the visible stars and gas do not provide enough gravity to explain the motion of everything inside the galaxy. Something unseen must be adding extra gravitational pull. Primordial black holes could be one possible explanation. If large numbers of these ancient black holes formed early in the universe, they might still be drifting through space today. You can imagine invisible objects scattered throughout galaxies, quietly adding extra gravity without producing any light. However, scientists are still investigating this idea. So far, evidence suggests primordial black holes might explain some, but probably not all, of dark matter. Detecting primordial black holes is extremely difficult because they would be small, dark, and often isolated in space. Unlike black holes in binary systems or active galaxies, these ancient objects might not interact with nearby stars or gas without surrounding material falling into them. They produce almost no visible signals. You can imagine trying to find a perfectly black marble drifting through a huge dark room. If nothing bumps into it or reflects light off it, you would never notice it was there. Astronomers search for clues in indirect ways. For example, they look for tiny changes in the brightness of distant stars when a hidden object passes in front of them and briefly bends the light. This effect is called gravitational microlensing. Even with these methods, finding primordial black holes remains extremely challenging, which is why their existence is still uncertain. Black holes might slightly distort the cosmic microwave background, which is the faint radiation left over from the Big Bang. This radiation fills the entire universe and acts like a snapshot of the cosmos when it was only about 380,000 years old. If black holes existed very early in the universe, their gravity and energy could have affected the surrounding matter and radiation. These effects might leave tiny imprints in the cosmic microwave background. You can imagine looking at a smooth pond surface. If a small pebble is dropped into the water, it creates ripples that disturb the surface. In a similar way, black holes in the early universe could create small disturbances in this ancient radiation. By studying extremely detailed maps of the cosmic microwave background, astronomers hope to find clues that might reveal whether early black holes helped shape the young universe. Astronomers believe many black holes may still be hiding inside the Milky Way, completely undetected. These hidden black holes are difficult to find because they do not emit light and may not be interacting with nearby stars or gas. If a black hole is drifting quietly through space without pulling material from anything nearby, it becomes almost invisible to our telescopes. You can imagine a perfectly black object floating through a dark room. If it does not reflect light or touch anything, you would not know it was there. Scientists suspect that thousands or even millions of these quiet black holes may exist in our galaxy. They might reveal themselves only when they pass in front of a distant star and bend its light slightly through gravity. Detecting these tiny effects helps astronomers slowly uncover the hidden population of black holes around us. Astronomers are still actively searching for hidden black holes throughout our galaxy and beyond. Because black holes do not emit light, scientists must rely on clever methods to detect their presence. One common approach is to watch how stars move. If a star suddenly begins orbiting an invisible object, it may be circling a hidden black hole. Another method involves detecting X-rays or other radiation produced when gas falls towards the black hole. Astronomers also look for gravitational effects, such as a black hole bending the light of a distant star as it passes in front of it. It's similar to noticing the wind by watching leaves move, even though you cannot see the air itself. With improved telescopes and new detection techniques, scientists are discovering more black holes every year, slowly revealing how many of these mysterious objects exist in the universe. In the extremely distant future, black holes could become some of the most dominant objects in the universe. This is because stars do not live forever. Over trillions of years, most stars will eventually burn through their nuclear fuel and fade away. Some stars will collapse into white dwarfs, neutron stars, or black holes after their lifetimes end. As time goes on, more and more black holes may form from these stellar deaths. Meanwhile, galaxies will slowly evolve, and many stars will disappear or grow dim. You can imagine a forest where trees gradually fall over time. Eventually, only the largest and most enduring structures remain. In a similar way, black holes may become some of the last massive objects left in the universe, long after most stars have vanished. These dark remnants could continue existing in the quiet, aging cosmos. In the extremely distant future, black holes may become the last massive objects remaining in the universe. Over trillions of years, stars will slowly run out of fuel and stop shining. Many of them will collapse into remnants, such as white dwarfs, neutron stars, or black holes. As time continues, even some of these remnants may disappear or cool down until they become extremely faint. Black holes, however, can survive far longer than normal stars. Because they do not rely on nuclear fuel like stars do, they can continue existing long after most luminous objects have faded away. You can imagine a city where the lights gradually turn off, one by one during the night. Eventually the streets become dark, but a few powerful structures remain standing. In a similar way, black holes may remain scattered across the universe long after most stars have disappeared. Even though black holes may survive longer than stars, they are not eternal. According to the theory of Hawking radiation, black holes slowly lose energy over extremely long periods of time. Every tiny burst of Hawking radiation carries away a small amount of the black hole's mass. At first, the loss is unbelievably slow, especially for large black holes. But as the black hole becomes smaller, the radiation process speeds up. Eventually, the black hole may shrink more and more quickly. You can imagine a large block of ice melting very slowly at first. As the block becomes smaller, the melting speeds up until the last pieces disappear quickly. Something similar may happen with black holes. In the incredibly distant future, after unimaginable spans of time, even these powerful cosmic objects may evaporate completely and vanish from the universe. The evaporation of black holes happens over timescales almost impossible to imagine. For a black hole with the mass of our Sun, scientists estimate it would take about 10 to the power of 67 years to completely disappear through Hawking radiation. To understand how enormous that number is, remember that the entire universe is currently about 13.8 billion years old. Compared to 10 to the power of 67 years, the current age of the universe is just a tiny fraction. It's like comparing 1 second to a time longer than the entire history of human civilization, repeated countless times. Even supermassive black holes, which contain millions or billions of solar masses, would last even longer, far beyond that already enormous number. This means black holes may continue existing for an incredibly long future, surviving long after stars, galaxies, and most other cosmic structures have faded away. Black holes remain one of the most mysterious objects in all of physics. Even though scientists have learned a great deal about them, many of their deepest secrets are still unknown. Astronomers can observe how stars move around black holes, how gas glows as it falls inward, and how gravitational waves are produced when black holes merge. These observations confirm that black holes truly exist and behave as predicted by many theories. But what happens inside a black hole remains one of the biggest unanswered questions. The laws of physics that work well in most parts of the universe may break down near the center of a black hole, where gravity becomes extremely strong. You can think of it like reaching the edge of a map where the landscape has not yet been explored. Because of this, black holes continue to challenge our understanding of the universe. One of the biggest puzzles about black holes is something scientists call the black hole information paradox. In physics, information about an object, such as its particles, structure, and energy, should never truly disappear. The laws of quantum physics suggest that information must always be preserved. However, black holes create a strange problem. When matter falls into a black hole, all the information about that matter appears to vanish beyond the event horizon. Later, if the black hole slowly evaporates through Hawking radiation, the radiation seems to contain no trace of the original information. Imagine burning a book and finding that the ashes and smoke contain no clues about the words that were written in it. This contradiction between quantum physics and black hole behavior is one of the deepest mysteries in modern science, and physicists are still working to solve it. The strange puzzle about information disappearing in black holes is known as the black hole information paradox. It arises because two important areas of physics seem to disagree with each other. Quantum physics says that information about physical systems should never be destroyed. Even if something changes form, the information about it should still exist somewhere. But black holes appear to do the opposite. When matter falls past the event horizon, all the details about that matter seem to vanish from the observable universe. Later, if the black hole slowly evaporates through Hawking radiation, the radiation looks random and does not seem to contain the original information. It's like putting documents into a sealed box that eventually dissolves into dust, yet the dust contains no trace of what was written inside. This paradox has become one of the most famous unsolved problems in theoretical physics. To solve the black hole information paradox, scientists believe we may need a deeper theory called quantum gravity. This theory would combine two major parts of physics: quantum mechanics, which describes tiny particles, and general relativity, which explains gravity and large cosmic objects. Right now, these two theories work extremely well in their own areas. Quantum mechanics explains atoms and particles, while relativity explains planets, stars, and black holes. But near a black hole's center, both sets of rules must apply at the same time. This creates a situation where our current theories start to conflict with each other. Imagine two different instruction manuals for the same machine that give slightly different directions. At some point, you need a new manual that combines both sets of instructions. Quantum gravity may provide that new framework, helping scientists understand what truly happens inside black holes. One idea scientists have proposed to solve the black hole information paradox is that information may not actually disappear inside the black hole. Instead, it could be encoded on the surface of the event horizon. The event horizon is the boundary where nothing can escape the black hole's gravity. According to some theories, the details about anything falling into the black hole might be stored on this surface like information written on a thin cosmic screen. You can imagine a security camera recording everything that enters a building. Even if the objects move inside and cannot be seen anymore, the camera still keeps a record of what passed through the door. In a similar way, the event horizon might preserve the information about everything that crosses it. This idea suggests that black holes may not destroy information after all, but instead store it in ways we are only beginning to understand. The idea that information might be stored on the event horizon led scientists to a surprising concept called the holographic principle. This idea suggests that all the information inside a region of space could actually be encoded on its outer boundary. A good way to picture this is by thinking about a hologram, like the one sometimes seen on credit cards or special stickers. A hologram is a flat surface, yet it can display a three-dimensional image. In a similar way, the holographic principle suggests that the three-dimensional contents of space might be described by information written on a two-dimensional surface. For black holes, that surface would be the event horizon. This idea is incredibly strange because it suggests that the universe might store information in ways very different from what we normally imagine, connecting gravity, quantum physics, and information in unexpected ways. According to the holographic principle, the information about everything inside a region of space might actually exist on its boundary surface, rather than inside the volume itself. This idea came from studies of black holes and how their information might be stored on the event horizon. Normally, we think of information filling the entire space inside an object. For example, a book contains its information on many pages stacked inside. But the holographic principle suggests something very different. It proposes that the full description of a three-dimensional space could be written on a two-dimensional surface surrounding it. Imagine a movie projected onto a flat screen. The screen itself is flat, yet it can show a world that appears three-dimensional. In a similar way, the boundary of space might contain all the information needed to describe everything happening inside. Black holes have inspired many new ideas about the deepest laws of physics. When scientists began studying how black holes behave, they discovered surprising connections between gravity, quantum physics, and information. These connections forced physicists to rethink many assumptions about how the universe works. For example, studying black holes helped lead to concepts like the holographic principle, which suggests that information about space might be stored on boundaries rather than inside volumes. You can imagine discovering that a simple object, like a key, also opens a door to an entire hidden room filled with new ideas. In the same way, black holes have become powerful tools for exploring the foundations of physics. By studying these extreme objects, scientists hope to uncover deeper rules that govern space, time, matter, and energy throughout the universe. Black holes revealed an unexpected connection between gravity and thermodynamics, the science that studies heat, energy, and temperature. At first, these two areas of physics seemed completely unrelated, but when scientists studied black holes more closely, they discovered that black holes behave in ways similar to objects that have temperature and energy. For example, black holes can slowly release energy through Hawking radiation, which means they act like objects that have heat. You can imagine a hot cup of coffee slowly cooling down as heat escapes into the air. Something similar may happen with black holes as they gradually lose energy over time. This discovery was surprising because black holes were once thought to be simple objects, defined only by gravity. Instead, they appear to follow rules that connect gravity, heat, and energy, revealing deep links between different areas of physics. Scientists discovered that black holes behave as if they have temperature and entropy, two important ideas from thermodynamics. Temperature usually describes how hot something is, while entropy measures how much disorder or information is contained in the system. At first, this idea seemed strange. A black hole appears completely dark and simple, so it might seem like it should have no temperature at all. However, the theory of Hawking radiation showed that black holes slowly emit tiny amounts of energy. Because they release energy, they must also have a temperature. Black holes also have entropy, which is related to how much information they can contain. You can imagine a sealed container holding many hidden objects. Even if you cannot see what's inside, the container still stores information about everything within it. In a similar way, black holes appear to store enormous amounts of hidden information. The discovery that black holes have temperature and entropy came from theoretical work by physicists in the 1970s. Scientists such as Jacob Bekenstein and Stephen Hawking realized that black holes must follow certain thermodynamic rules. Bekenstein first proposed that black holes should have entropy, meaning they store information about the matter that falls into them. Hawking later showed that black holes should also emit tiny amounts of radiation. Together, these ideas transformed how scientists think about black holes. Before this work, black holes were often viewed as simple objects, defined only by mass, charge, and spin. But the new research suggested they behave more like physical systems with energy and temperature. It was like discovering that a seemingly silent machine actually has hidden internal processes. These breakthroughs opened an entirely new field called black hole thermodynamics. One of the most surprising discoveries about black holes is that their entropy depends on the surface area of the event horizon, not the volume inside it. In most physical systems, entropy grows with volume. For example, a larger box can hold more particles and therefore more information, but black holes behave very differently. Physicist Jacob Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon, the invisible boundary surrounding it. This means that as a black hole grows, its information capacity increases with the size of its surface. You can imagine writing information on the surface of a sphere rather than storing it inside the sphere. This strange rule suggests that the boundary of a black hole plays a much deeper role in physics than scientists once thought, hinting at hidden connections between gravity, space, and information. The strange relationship between black hole entropy and surface area suggests a deep connection between gravity and information. In everyday situations, we usually think of gravity as a force that pulls objects together, like Earth pulling us toward the ground. But black hole studies hint that gravity might also be linked to how information is stored and organized in the universe. Because a black hole's entropy depends on the area of its event horizon, scientists began to suspect that information about matter and energy may be connected to the geometry of space itself. You can imagine writing data on the surface of a hard drive. The arrangement of that surface determines how much information can be stored. In a similar way, the structure of space-time might determine how information exists in the universe. This idea has inspired many new theories about the fundamental nature of reality. Black holes may hold important clues about the fundamental structure of space-time itself. Space-time is the combined fabric of space and time that makes up the universe, and gravity bends this fabric around massive objects. Near a black hole, this bending becomes extremely intense. Space can curve dramatically, and time can slow down compared to regions far away. Because these effects become so extreme, black holes allow scientists to study situations where the normal rules of physics begin to break down. You can imagine testing a bridge by placing heavier and heavier loads on it to see how the structure responds. Eventually, the test reveals the true limits of the design. In a similar way, black holes push space-time to its limits. By studying them, scientists hope to understand the deeper rules that govern how space and time are built. Some theoretical ideas suggest that black holes might contain wormholes, which are hypothetical tunnels connecting distant regions of space. A wormhole would act like a shortcut through space-time, allowing travel between two faraway points, much faster than normal travel through space. To picture this, imagine an ant walking across a sheet of paper from one corner to the other. The journey takes time because the ant must cross the entire surface, but if you fold the paper so the two corners touch, the ant could cross instantly through the fold. A wormhole would work in a similar way for space itself. Some mathematical solutions in Einstein's equations allow for these tunnel-like structures. However, there is currently no direct evidence that real wormholes exist inside black holes. For now, they remain an interesting theoretical possibility, being studied by physicists. Some theories suggest that black holes might connect very distant regions of space through structures similar to wormholes. In these ideas, a black hole could act as one entrance to a tunnel in space-time, while another location somewhere else in the universe forms the exit. This concept comes from certain mathematical solutions of Einstein's equations. These solutions show that space-time could theoretically bend and connect distant places in unusual ways. You can imagine a long highway across a country. Normally, traveling from one city to another might take many hours, but if a hidden tunnel suddenly connects both cities directly, the trip becomes much shorter. A wormhole would work in a similar way, creating a shortcut through space-time. However, these ideas remain highly theoretical, and scientists still do not know whether such connections could exist in reality. Many of the ideas about wormholes and strange connections inside black holes remain speculative. This means they come from mathematical theories and models, rather than direct observations. Physicists use equations from Einstein's theory of relativity to explore what might be possible in extreme conditions. Some of these equations suggest unusual structures like wormholes could exist. However, solving an equation does not always mean the object actually exists in nature. You can think of it like designing a machine on paper. The design might work perfectly in theory, but building it in the real world may turn out to be impossible. In the same way, wormholes and other exotic structures predicted by black hole theories may require forms of matter or energy that we have never observed. Because of this, scientists continue to study these ideas while searching for real evidence. Black holes continue to challenge our understanding of physics more than almost any other object in the universe. They combine extreme gravity, high energy, and strange effects involving space and time. Many of the laws of physics work very well in everyday situations and even across most of the cosmos, but near a black hole, especially near its center, these laws begin to reach their limits. For example, general relativity describes gravity and large cosmic structures very accurately, while quantum mechanics explains the behavior of tiny particles. Yet near a black hole, both theories must apply at the same time, and they do not always agree. It's like having two rulebooks that work perfectly on their own, but give different instructions when combined. Because of this conflict, black holes are helping scientists search for deeper theories that could unite these fundamental laws of physics. Studying black holes is extremely challenging because they cannot be seen directly. Since light cannot escape their gravity, astronomers must rely on advanced telescopes and detectors to observe the effects black holes have on their surroundings. Scientists often watch how nearby stars move or how gas glows as it spirals into the black hole. They also detect powerful signals like X-rays, radio waves, and gravitational waves produced by matter falling inward or by black holes merging. It's similar to figuring out where a hidden fan is in a dark room by watching how dust moves through the air. Modern observatories on Earth and in space allow astronomers to study these subtle clues. Instruments like radio telescope networks and gravitational wave detectors provide new ways to investigate black holes, revealing details that were impossible to observe just a few decades ago. Every time scientists study black holes more closely, they often discover unexpected phenomena. These objects behave in ways that sometimes surprise even experienced researchers. For example, astronomers have observed stars orbiting black holes at incredible speeds, jets of particles stretching across millions of light years, and gravitational waves traveling across the universe after black holes collide. Each new observation reveals details that were once only theoretical. You can think of it like exploring a deep ocean trench. The deeper explorers go, the more strange and fascinating creatures they discover that were never seen before. Black holes create a similar situation for astronomy. As telescopes and detectors become more advanced, scientists continue uncovering new behaviors and extreme conditions that challenge current theories. These discoveries help expand our understanding of how the universe truly works. Black holes remain one of the most fascinating mysteries in the entire universe. Even after decades of research, scientists are still uncovering new details about how they form, grow, and interact with the surrounding cosmos. We now know that black holes exist in many sizes, from stellar black holes formed by collapsing stars to supermassive giants, weighing billions of times more than the Sun. We have even detected the ripples in space-time created when black holes collide. Yet the deepest questions remain unanswered. What truly happens inside the event horizon? How do gravity and quantum physics work together in such extreme environments? Could black holes reveal a deeper theory of the universe? You can think of black holes as cosmic laboratories, where the universe pushes its laws to the limit. By studying them, scientists hope to unlock some of the most fundamental secrets of reality itself.